Welcome to this course on fiber optic communication, and in this course now we are going to discuss more advanced topics, the nonlinear fiber optics. Up till now whatever we have discussed, that falls into the category of linear fiber optics. What that means is that the medium properties, the fiber properties do not depend upon the signal. On the other hand, when the material properties are modified by the signal itself, then that falls into the category of what is called nonlinear fiber optics. So, now onwards for next couple of lectures, we are going to discuss the propagation of light in the optical fiber, taking into consideration the nonlinear effects. The simple question one can ask is that if the medium properties change, what will happen to the signal propagation? Take a simple example. Let us say we want to transmit a pulse on the optical fiber. When the pulse was propagating in the linear domain, then the properties of the propagation are decided just by the medium properties. We could write down the wave equation. We can solve the wave equation without worrying about what is the amplitude of the pulse, and we get the modal distribution, we get propagation constant, and from that we can find out the propagation characteristics of a pulse. Imagine now that the medium properties are modified by the pulse itself, and let us say that the refractive index of the optical fiber is related to the intensity of light. And for a simple example, let us assume that the refractive index increases with the intensity of light. What it means is that now the whole pulse is not going to see the same propagation parameters, because at the center of the pulse where the light is intense, the refractive index seen by the pulse is different than on the edge of the pulse where the light is less intense, and because of that the refractive index is lesser compared to the refractive index seen by the pulse at its center. So, you require actually a whole new framework for analyzing these problems, and that is what precisely we are going to do in next couple of lectures, that if the medium properties are altered by the signal itself, what will happen to the propagation of a pulse. Second thing one can see later on, that when the nonlinear effects are present in the optical fiber, a continuous signal propagation is unstable. What that means is, even if I try to send a continuous signal in the optical fiber, any small perturbation will break this signal into pulses. That means, without taking into consideration the pulse nature of the signal, the nonlinear propagation will not be very effective. So, in this lecture, first of all we will have a basic formulation. We will also ask a question, why nonlinear fiber optics is important? Is it only a question of academic interest, or is it becoming more and more important to include the effect of nonlinearity into fiber optic communication? And if at all yes, then can we make use of these nonlinear effects to improve the signal propagation from optical communication point of view? So, let us take a very basic model. What is the dielectric constant of a medium? When the electric field is imposed on a dielectric material, there is induced polarization in the material, which is given by the susceptibility of the medium, and normally we consider only the first order susceptibility, which gives the dielectric constant of the medium. However, this is just an approximation. In real situation, if the light of intensity is large, then the first order term which gives dielectric constant is not adequate, and you have to also consider the higher order terms into the polarization of the material. So, in general, then one can say that the induced polarization in the material, this P is given as epsilon 0, which is the free space permittivity, the first order susceptibility, which is given by chi 1 E is the imposed electric field, plus the second order susceptibility given as chi 2 given as E plus third order susceptibility E plus so on. So, normally this is the dominant term, which is chi 1 susceptibility, and this one is contributing to the dielectric constant. So, this is the dominant term, and this contributes to dielectric constant. The second term, where you will see now that the polarization is related to E and E, and this quantity now is a tensor. So, basically what we are saying is that the dielectric constant, when we include this term, has an effect of electric field itself. However, for material like glass, this is a symmetric molecule. So, chi 2 is generally negligibly small. So, this quantity for SiO2 for glass is small. The third term here, which is the third order susceptibility, which now says that the refractive index is proportional to the square of the electric field, and that is the one which is going to contribute to the nonlinear effects in the optical fiber. So, this term is in the glass will contribute to non-linearity. So, now if you take a simple case, then we can say that the refractive index of the medium in the presence of non-linearity, it is a function of omega because of the dispersive nature of the glass itself. The chi 1 actually is a complex quantity, it is a function of frequency which gives dispersion effect, at the same time it gives attenuation also. So, this quantity is a complex quantity. And let us take a very simple case where this term, the refractive index is proportional to mod of E square. So, we have this is a term which is a non-linear term where non-linearity is not included, plus you are having a non-linearity term is N2 mod of E square. This term N2 is what is called the non-linearity coefficient. And this is material dependent. So, for different materials you will have different values of N2, the non-linearity coefficient, and this quantity actually is related to this third order susceptibility of the medium. So, if I write in terms of the third order susceptibility, this quantity N2 is equal to 3 by 8 n into chi 3, the third order susceptibility. And for the glass, this value is approximately 2.3 into 10 to the power minus 22 meter square per volt square. If you really look at this number and compare this number with other materials, you will find that this number is about 2 orders of magnitude smaller than what you see in many other materials. One can then ask a simple question: if the glass nonlinear coefficient is 2 orders of magnitude smaller than the other well known material which have good nonlinearity, should this nonlinearity effect be considered in optical communication or not? And this question can be answered by comparing how the nonlinear effects are manifested in the bulk material and in the optical fibers. Is there any situation difference? A nonlinear effect, when you see in the bulk material, the light beam enters the bulk material, there is a size of the bulk material, and the nonlinear interaction between the light and the matter takes place in that bulk material, whatever size is given to you. On the other hand, when the light enters the optical fiber, it travels a very long distance inside the optical fiber. So, it keeps interacting with glass. So, you have a cumulative effect of the nonlinearity in the optical fiber. So, one can just do a quick comparison and see how much enhancement of nonlinear interaction takes place inside the optical fiber compared to a bulk material. So, let us say, let us define something called a figure of merit for nonlinear interaction. And this figure of merit is, call it, let us say, some efficiency parameter. So, let us say some eta. This is now decided by the product of two quantities, the intensity of light I and the interaction length. So, this is the light intensity and this is the interaction length. Now, light intensity is nothing but the power density per unit area. So, this will be watts per meter square, and this is the interaction length, which is in terms of say meters. So, if you want to increase the efficiency of nonlinear interaction, either I can increase the intensity of light or I can increase the effective length of interaction, or both if they are possible. So, let us say if I have a certain light beam available to me and we want to increase the light intensity, what will normally come to your mind? Immediately it strikes you that I can take the light beam and focus this light beam by using some lens or something, and then the light intensity is enhanced. So, by focusing of the light, the spot size becomes smaller and smaller, and then the light intensity can be enhanced. So, if I have a Gaussian light beam, and let us say the spot size which is created by the light beam is, let us say, W0. So, the intensity of light, this I, will be the power which is in the optical beam divided by the area of the spot, which is pi W0 square, where this quantity W0 is the spot radius. So, I have a Gaussian beam which is like that, and that is where the spot size which you have here, which is equal to 2 times W0. But now, as we are tightly focusing this spot, you will see that the length over which this focus region is, that is related to this size of the waist. which is the spot size. So, in a bulk medium, when I tightly try to focus the optical beam, the interaction length also get affected, and the interaction length in bulk optics effective is pi W 0 square divided by lambda. So, the product of the two quantities, the figure of merit what you have defined in the bulk medium, if we take this is eta bulk, that is equal to I times L effective, that is equal to the power divided by pi W 0 square times pi W 0 square divided by lambda. So, that is equal to P divided by lambda. What that means is that the figure of merit or the interaction efficiency in the bulk material is independent of the focusing conditions, because if you have a loose focusing, the interaction length is more, but then the spot size is also very large. If you try to reduce the spot size, you tightly focus it, the interaction length also gets affected, and the product of these two are independent of the focusing parameter. That is the situation in a bulk material. So, that means in bulk material, if we want to enhance or if we want to find the effect of nonlinearity, and if you want to do a certain wavelength, only option you have with you is to increase the optical power, and that is what people do. If they want to study the nonlinear effects in bulk material, they require intense optical beams, because by that only the nonlinearities can be induced effectively and you can study those nonlinearities. Let us compare this situation with the optical fiber. So, first thing we will notice that inside the optical fiber, when the light gets in, the light remains focused or confined to a region which is the size of the core. And then, since the loss on the optical fiber is very, very small, that intensity reduces, but it reduces slowly, and that intensity remains practically constant over some tens of kilometers. So, in this fiber case, if you want to write down, if the radius of the fiber is, let us say, A, and the attenuation constant is given by alpha, the I, which is the intensity of light inside the optical fiber, is P divided by pi A square. Because as I said, when the light gets inside the optical fiber, it remains confined to the size of the core. So, intensity is P divided by pi A square, where A is the radius of the optical fiber core. We can say it is the core radius. When the light propagates inside the optical fiber, it exponentially decays. So, if I have P as a function of some z, that is equal to some initial value e to the power minus alpha z, where alpha is the attenuation constant, we can also call it power attenuation constant. So, then if you take a distance which is 1 over alpha, that is where the power will reduce to 1 over e of its initial value. That means, effectively one can say that the light is having that intensity over a distance which is approximately equal to 1 over alpha. Or in other words, for the fiber case, we have L effective, which is approximately as 1 over alpha. So, if I write down what is the figure of merit for the fiber, that will be equal to this into this. So, it will be P divided by pi A square into 1 upon alpha. So, if I ask how much interaction efficiency is increased inside the optical fiber compared to the bulk material, I can just take a ratio of these two quantities. So, one can say that we have this fiber divided by eta bulk material, and that is equal to this quantity p divided by pi square alpha. So, p divided by pi a square alpha divided by the eta bulk, which is p upon lambda. So, you can put p upon lambda. So, this is equal to lambda divided by pi a square into alpha. Let us put some parameters now for a typical optical fiber. So, let us say I have a single mode optical fiber where the core size is of the order of about 4 micron. So, 4 to 5 micron or something like that. So, let us say A, I take let us say of the order of 2 micrometer. The alpha, which is 0.2 dB, equal to 0.2 dB per kilometer, that is equal to 0.2 into 10 to the power minus 3 dB per meter. This can be converted into the Napier values. So, if I do that, that will be let us say approximately about 8 into 10 to the power minus 5 per meter, and lambda, let us say we take 1550 nanometer. So, 1550 nanometer, which is equal to 1.55 micrometer. So, if I take these values for A, alpha and lambda into this expression, you will see that this ratio here, that will be equal to approximately about 10 to the power 9. Now, this is interesting, because what this means is for the same parameters, same value of optical power, the nonlinear effect inside the optical fiber is enhanced by 1 billion times than what you can see inside a bulk material. Just to give numbers, what that means is whatever effect you can see in the bulk material with let us say 1 watt of power, the same effect inside the optical fiber can be seen with 1 nanowatt of power. And normally when people conduct experiments for bulk optics, certainly people have the power in that range of few watts. So, that means the power which we are dealing in optical communication, which could be the order of about microwatts, milliwatts, the nonlinear effects are certainly going to be present, because that power, once it is confined to the optical fiber, that will keep interacting with the material over long distances of tens of kilometers. So, now it makes a very strong case. What that means is that the propagation of light inside the optical fiber ideally is incomplete without taking into consideration the effect of nonlinearity, because the nonlinear effects are going to be present, and when the light starts propagating inside the fiber, it will keep affecting the signals. One may also note that when it was a single channel transmission, maybe the total power which was confined inside the optical fiber was small. Each channel used to carry let us say maybe of the order of about few milliwatts of power. But when we are talking about a multi-channel WDM system, if each channel has to carry a power of milliwatt and let us say 100 channels transmit, inside the optical fiber the total power will be about 100 milliwatts. The number can go still higher. What that means is that as we are going to go to more complex optical communication system with multi-channel transmission, the power density inside the optical fiber certainly is going to be large enough to really worry about the non-linearity inside the optical fiber. And that is the motivation, that if the nonlinear effects are going to be present in the optical fiber even for the moderate powers, then instead of ignoring these effects, the better approach would be to understand what these nonlinear effects are doing to the propagation of signal and try to make use of these nonlinear effects for improvement of the quality of the signal. So, in last 2 decades, essentially there has been significant emphasis in investigating the effect of nonlinearity in the signal propagation in the optical fiber. So, nonlinear effects actually give various phenomena. They give modification of the pulse, they can also give different generation of frequencies, because as we saw in the polarization we are having a product term of E and E. So, if you are having 2 different signals, 2 different frequencies, then the nonlinear effect may generate some third frequencies. So, you have a new generation of frequencies. You can have a second harmonic generation inside the material because of nonlinearity. So, you have a variety of phenomena which are going to be seen inside the optical fiber once the nonlinearity is invoked. So, let us first look at a simple model with a nonlinearity where the refractive index, nonlinear refractive index is proportional to the mod E square, and mod E square is proportional to the Poynting vector or the power density. That means, we are considering a simple case where the refractive index change is proportional to the power density inside the medium, inside the optical fiber, and that is what is called the Kerr nonlinearity. So, in our analysis we essentially are going to confine ourselves to the Kerr nonlinearity, and that is what as we saw here, this quantity, since you are having the nonlinear refractive index which is proportional to E square, this nonlinearity we call as the Kerr nonlinearity. So, in our analysis to start with, we will just focus only on this nonlinearity, and later on then we will talk about the other effects also as we proceed in our discussion. So, now to make the analysis of the propagation of light inside the optical fiber in the presence of nonlinearity, we have to again start from the very basic equations, the Maxwell's equations, because now the wave propagation which you have studied so far is now going to be completely altered, because the Maxwell's equation are going to be modified, because now if you look at the displacement which is related to the polarization has a nonlinear term. So, the displacement will have a nonlinear term, that nonlinear term will get reflected into the wave equation. So, the wave equation will become nonlinear. So, you require a fresh approach to investigate the signal propagation in the optical fiber where nonlinear effects are present. So, that means we have to again start from the basics of writing down the wave equation and then try to make certain approximations, so that the equation becomes solvable, and then we can see how one can investigate the signal propagation in the optical fiber. One more thing to note here, that the effect which we are talking about here, the nonlinear effect, when it is cumulative over long distance, it becomes large enough inside the optical fiber. But if you consider a short distance, the effect intrinsically is a very weak effect, it is not a very strong effect. So, if for a short distance if the signal travels, one can assume even for the moderate light power inside the optical fiber, that nonlinearity can be neglected. Only thing is, the small pieces when you accumulate together, then the nonlinear effect will become significant. But since intrinsically this effect is weak, the equation can be approximated. There are certain terms, higher order terms in the equations can be neglected. So, the equations become little more tractable, and then one can solve those equations to study the propagation of light inside the optical fiber. So, let us start the basic equations, the Maxwell's equations. So, let us start with Maxwell's equations. So, we have del cross E, that is minus d B by dt, and that is if we assume that the permeability is not varying as a function of time, we can write that as minus mu 0 d h by dt. Also, since we are dealing here with the dielectric media, we can assume that the permeability of the medium is same as the free space permeability, which is mu 0. The second Maxwell equation del cross H is equal to dd by dt, because we are assuming here that the conductivity of the medium is 0. So, there are no conduction current flowing. So, we are saying here J is identically equal to 0. We can have a third equation, which is del dot D is equal to the charge density, but again we may assume here there are no free charge densities. So, this quantity is also 0, because the rho is also identically taken as 0. And fourth equation del dot B is equal to 0. And as we have seen, now in this case the D, the displacement, is now epsilon times E plus this polarization, which is the polarization expression which we talked earlier. So, now the P is actually given by this. So, as I said earlier, normally when the intensities are not very large, these terms are negligible, and this is the only term which is there. So, epsilon 0 times chi 1, that is the term which will be here, and then we can write down 1 plus chi 1, that is the quantity which will give you dielectric constant of the medium. So, in normal situation, this will be equal to epsilon times E plus epsilon times chi 1 times E. And other terms are neglected. So, that will be equal to epsilon 0 times 1 plus chi 1 times E. This is the linear case, because we have neglected the other terms which are coming here into the polarization, the second order susceptibility and third order susceptibility. So, the displacement now is given by this. So, this quantity is nothing but the dielectric constant of the medium. That is what we have been talking all through, that the fiber has a dielectric constant, and as we know that this quantity dielectric constant, if you are having a loss in the medium, then this quantity becomes a complex quantity. So, in general this quantity actually is a complex quantity. So, which is a complex quantity, and imaginary part of this gives what is called the attenuation constant. Let us now do this same thing what we normally do for the wave equation. You can take curl of this equation and substitute from this. So, we can say del cross E that is equal to minus del cross mu 0 d h by dt. By interchanging the del and d by dt, this you can get as minus mu 0 d by dt of del cross h, and you can substitute for del cross h from this equation from here, which is d by dt. So, this will be equal to minus mu 0 d by dt of d by dt. If I substitute for d in terms of polarization, this will be minus mu 0 d 2 by dt square epsilon times E plus the polarization. We can separate out these two terms. So, that is minus mu 0 d 2 epsilon 0 E by dt square minus mu 0 d 2 p by dt square. And now, as you have seen, this p has now the linear and a nonlinear term. So, p now is given as epsilon 0 chi 1 times E plus, since we are dealing with a medium which is glass, I am saying the second order susceptibility is negligibly small. So, let us ignore that. So, you have a third order susceptibility, which is chi 3 E E E. So, we can call this quantity is the linear polarization and this quantity as the nonlinear polarization. We can take this quantity now P L and P N L and substitute into this, and also expand with the third triple product. We can get del of del dot E minus del square E is equal to, when I take this quantity here, the epsilon 0 can be taken out. So, you have a mu 0 epsilon 0, but if you recall 1 upon square root mu 0 epsilon 0 is the velocity of light in vacuum, which is c. So, this thing can be written as minus 1 upon c square d 2 E by dt square minus mu 0 d 2 P L by dt square minus, no, plus, minus is taken out, d 2 P N L by dt square. Now, from the Maxwell's equations, this quantity del dot D is equal to 0, because the rho is equal to 0, and since epsilon is not varying as a function of space. So, this also gives you del dot E is also equal to 0. So, this quantity will identically go to 0, and that will give us then the wave equation, which will be, so wave equation which will be del square E minus 1 upon C square d 2 E by d t square, that is equal to mu 0 d 2 P L by d t square plus mu 0 d 2 P n L by d t square. So, note here now that when the nonlinear terms were not there, this quantity would not be there, and then this would reduce to the normal standard equation, which we already solved for the wave propagation in the optical fiber. However, now we are having a term which is an additional term here, which is P n L, and P n L, as we know, depends upon the electric field itself. So, you are having this quantity which is given by this. So, actually this quantity which is the nonlinear term, that is what now is going to come into picture because of this third order susceptibility. To solve this equation now, let us consider the simple time harmonic fields. So, let us say the electric field E is given by some E 0 e to the power j omega 0 t, where omega 0 is the signal frequency. Now, one can show that if you are having a pulse width which is smaller than about 10 nanoseconds, then you have dispersive as well as nonlinear both effects present. If you are having the pulse width which is larger than about 10 nanosecond, then you will see the nonlinear effects, but in the range of about 10 nanosecond to about 10 femtoseconds, you will see both the effects of dispersion and nonlinearity will be present, and the pulse propagation will be decided by the simultaneous effects of these two. So, essentially our interest now is that if you launch a pulse of light inside the optical fiber, what way the pulse is evolved as it propagates inside the optical fiber. So, as I mentioned earlier also that here we are not now looking at only the continuous propagation of light, we are actually interested in investigating the pulse propagation of light. So, the light is having a carrier frequency which is omega 0, but it also has an envelope in the form of pulse. So, carrier will have certain propagation characteristics, but we are more interested in finding out the evolution of the envelope of this pulse. That is what our prime interest is. So, that is what essentially we would like to investigate, that when a light pulse is launched inside the optical fiber, what way the pulse evolution takes place. Now, to study the pulse evolution in the optical fiber, it is easier to first express the electric field which are in terms of time as a function of frequency or in the spectral domain. So, the electric field actually if you see, it is a function of the space and time. However, since we are talking about a narrow band signal around this frequency which is omega 0, one can redefine this problem in terms of the frequency domain. So, let us say that I define the Fourier transform of the electric field, which is a function of r, which is the space, and omega minus omega 0, so the frequencies around this carrier frequency omega 0, and that is minus infinity to infinity. The electric field is a function of space and time, e to the power minus j omega minus omega 0 t dt. So, this is the Fourier transform. So, E tilde is the electric field in the frequency domain. So, if I take the electric field as a function of space and time, and I am taking the Fourier transform as a function of time. So, here I see essentially the spectrum of the electric field as a function of distance r. So, the wave equation now can be written, if I take this quantity and write in terms of the Fourier transform, the wave equation del square E tilde plus epsilon as a function of omega k naught square E tilde equal to 0. Now, note here all these quantities, the nonlinear effects and dispersion and whatever the parameters are there, essentially we have captured into this quantity, which is this quantity epsilon. So, one can define this effective dielectric constant, which takes into consideration the linear as well as the nonlinear effects and also the frequency variation. So, here this epsilon omega is equal to 1 plus the chi 1 which is a function of omega, and this quantity as we already said is complex, because there will be loss in the medium, plus you are having the nonlinear effects which can be given by epsilon nonlinearity. So, whatever we have written here essentially can be written effectively in this form. Now, we can apply separation of variable to solve this wave equation, and as we already said that now you are going to have a signal which is not only a continuous signal, but you have a signal which has an envelope, it is in the form of a pulse. That means, the electric field, if I write as a function of space and omega minus omega 0, has a spectral band now. So, that is given as some function f which is of transfer coordinates rho and phi, has an envelope spectrum which is a function of z omega minus omega naught and a phase term e to the power minus j beta 0 z. So, what you are saying here, let us say this is the optical fiber, in the radial direction here this is rho, this direction is phi, this direction is z. So, we are saying the electric field is given by a product of a function which is in transverse plane, which is rho and phi, that is this quantity, and this is the envelope which is now evolving as a function of z. So, you are having a band of frequencies which are going to be altered as the signal propagation takes place along the optical fiber, and the whole thing is moving with a phase constant which is equal to beta 0. So, you are having a travelling wave kind of phenomena which is taking place here, it has an envelope. So, you have a situation, you have a pulse here which is like this, then you are having the carrier frequency inside this. So, this is carrier frequency is omega 0, this is the envelope function which you are seeing here, the frequency domain, and this is the phase constant corresponding to the center frequency which is omega 0. Now, if I substitute this function into the wave equation and separate out, you will see two equations. One which will give the transverse fields f, that is equal to plus here epsilon omega k naught square minus beta f is equal to 0, and second equation which we will get for the envelope, that is minus 2 j beta 0 d A by d z plus tilde square minus beta 0 square A, that is equal to 0. Now, note here that this equation is a simplified equation. So, you have a term here which is d 2 A by d z square also, because when you are having the wave equation, this equation here, we are also going to get d 2 z by d 2 by d z square of E. However, since the evolution of the pulse is slow, as we already said, this is a weak phenomena which we are talking about, this quantity is negligibly small. And therefore, for as an approximation, we can say that the evolution of the pulse essentially is given only by this term. The second order effects are negligibly small, and the transverse fields are essentially governed by this equation. So, essentially we have to now solve these two equations together to get a comprehensive equation which will tell us how the pulse evolution is going to take place. So, in the next lecture, when we meet, essentially we will take these two equations, try to substitute some parameters into this and see what finally the equation arises, which then can be solved to study the evolution of the pulse on the optical fiber. So, let me summarize what we have done today. First of all, we showed that when the light is intense, that time the induced polarization has higher order susceptibility terms also, they cannot be neglected. For the material like glass, the second order susceptibility contribution is negligible, because the SiO2 molecule is symmetric. So, the third order susceptibility is the one which contributes to the nonlinear effects. Then we saw that even if the glass is not a very good nonlinear material, because its nonlinear coefficient is 2 orders of magnitude smaller compared to many well known nonlinear materials. Since the interaction length inside the optical fiber is very large, the nonlinear effects are very pronounced inside the optical fiber. So, the compared to the bulk material, the interaction efficiency is a billion times more inside the optical fiber approximately. So, there is a strong case to investigate the nonlinear effects inside the optical fiber. Then we started with the Maxwell's equation and wrote down the Maxwell's equation and the wave equation in terms of the polarization, which includes the nonlinear terms. So, next time when we meet, then we solve this nonlinear equation to see the effect of pulse propagation.